All right, so now I wanted to look at a couple of different examples, one using an elliptical region, and then I also want to do one with a function of 3 variables. So these are both going to be things that are harder to visualize, which is good because we want to do some practice where we're just relying on the math, because pictures are nice, but they're not always accessible, right? A lot of we can be working on some problems that have a pretty gross region or something like that, which would be very hard to visualize. Okay. So this one looks like this. So ellipse equations look pretty similar to the circle equations, except for they usually will be divided by something. I don't even remember exactly off the top of my head exactly how the ellipses work. Like something like one of the radii is going to be one of them's going to be like a half or something like that. But it doesn't matter because, like I said, we're going to do this without relying on the picture. Okay. So let's go ahead and just look at the partial derivatives first. Okay. So this is going to be negative 2x. So that's just going to give us x equals 0. So the critical point should be pretty easy here. And actually, this should be less than or equal to 1, right? If it was just equal to 1, then you just need to look at the boundary itself, which sometimes it does give you conditions like that where you're just looking at the boundary. So that would mean something like this. This is inside of the ellipse, so therefore it wouldn't be in consideration, right? It's not on the boundary. And then this one should also be 0. So this one's pretty easy. We don't actually have to do anything there. So f of 0, 0 is equal to 0, of course. So that is in consideration there. So we'll go ahead and again solve this boundary. It doesn't really matter whether you do this for x or for y. It might actually be slightly easier to solve it for x, because then x is going to be equal to 4 minus 4y squared, the square root of that, right? Because you're going to have 1 minus y squared, multiply it by 4, and then take the square root, which you could simplify to 2 over 1 minus y squared, right? And it should be plus or minus here as well. And it should say x, not x squared. So plus or minus 2 root 1 minus y squared. Okay. So this is the, so the plus part would be the top half of the ellipse. The minus part would be the bottom half of the ellipse. It's still centered at 0, 0. So it's still going to be symmetric, right? If it's not centered at 0, 0, then it might not be symmetric like the last one was. And then you have to pay more attention to the 4 distinct points here. Okay. This one I don't have the answer for, so we're actually going to plug all the points in and everything to make sure that everything is correct. So let's go ahead and plug this in then for our function. So we're going to have f of, we'll do the positive one first, 2 minus y squared y is equal to 2 root 1 minus y squared squared over 4 plus y squared, or I'm sorry, I'm looking at the restriction, not the actual function. So this should be negative that, and that's fine. Yep, and then that's the same thing. Okay, so we can simplify this a little bit though, right? Because this will be 2 squared is 4, then the 4's will cancel. So actually that's kind of weird, because this is just equal to 1 now. So this actually is going to change the problem a bit from what I was expecting, because this is actually going to cut out a lot of the work, right? Because now we don't have any critical points. because the function is constant on that boundary. Right, so it's, I mean, we can just, or sorry, I forgot this negative up here. Right, so that's going to make this whole part negative. So yeah, so we'll square this. This will be 4 divided by 4. This will be 1 minus y squared, but then we have the negative out front here. So this is going to be 2y squared minus 1. Okay. So a more typical problem then. All right, so now we want to take the derivative. Let's call that gy. So g prime of y will be 4y. We'll set that equal to 0. Okay, so this will imply that y is equal to 0. So we want to check this point. So when y is equal to 0, x is going to be 2 times 1 minus 0, square root of that, so 2. Okay, so we have the point 2, 0 that we'd want to check. Okay. So f of 2, 0 is going to be 0 minus 2 squared, which is negative 4. Okay. So now if we look at the other side, we plug in the negative 2 root 1 minus y squared. This part's going to be exactly the same, right? So everything's going to be the same here. We're still going to get y equals 0. What's going to be different is going to be the sign of the x value, right? So that's going to be f of negative 2, 0 instead. But ultimately, this is going to be the same thing, right? This is still going to be negative 4. So we have a tie here. So then the last thing we would need to check here are the boundary points of this ellipse, right? For each side of it, because this is like, again, it looks something like this. So we're actually cutting it off into halves this way since we did the y's. So we're looking at, like, this is the positive 2 square root of 1 minus x squared part, and then the other side is the negative. So we need to check these boundary points, which is going to be where y equals 1 or y equals negative 1. Okay. So we'll go ahead and do that here. So f of, well, when y equals 1, x is going to be 0, right? Just plug in 1 here. So 0, 1, so that's going to be 1 squared minus 0, which is going to be 1. And then negative 1 is actually going to be the same thing. So negative 1 squared minus 0, so we still get 1. And our critical point was at 0. So that means these right here will be the global minimums. Okay, and these right here will be the global maximums. Okay, and that's going to be it for that one. So just to recap here, so we needed critical point, substitute the function so that you have it just in terms of one variable according to your restriction, then find the critical point of that, right? And then look at the boundary points of that restriction that we cut off there. Okay.